Thank you. Hello, everyone. My name is Anca-Cristina. I'm an assistant professor at the University of Texas at Austin. My presentation today is on ASR-induced anisotropy in the mechanical properties of concrete. This work was done at the University of Toronto, where Professor Frank Vecchio was my advisor. This was done during my doctoral studies. Why did we do this work? We can see in this image an image of an ASR-affected reinforced concrete bridge here in US. It had to be demolished, its replacement costing hundreds of millions of dollars. When faced with such a case, engineers need an assessment tool that would help us to evaluate the safety and the serviceability of such a structure. And so the work that I'm presenting today is an effort towards developing such a tool. Here's the outline of my presentation. I will begin with a brief introduction, followed up by the experimental and analytical programs that we undertook in order to better understand and to better characterize the mechanical properties of ASR-affected concrete. I will then continue with the validation studies that were performed, and I will end with conclusions. Alkali-silica reaction, ASR, is a harmful deteriorating mechanism affecting the performance of concrete structures worldwide. It develops when the concrete mix contains reactive aggregates that are susceptible to alkali attack. The alkali hydroxides present in the cement paste, they react with certain minerals within these aggregates, causing a gel, which in the presence of moisture expands and cracks the concrete matrix. We can see in these lower images some crack patterns that we may encounter out there of infrastructure suffering from ASR. ASR-affected structures, they may pose several issues, and one of them is increased seismic demand. Because of the ASR-induced expansion, we expect an ASR-affected structure to exhibit a higher seismic demand compared to a similar non-reactive structure. And this is because of the pre-stressing effect that ASR has on the reinforcement. In continuing to discuss ASR-related structural implications, there are two distinct mechanisms that we need to be mindful of: the ASR-induced pre-stress that I just mentioned, and the accompanying deterioration of the concrete mechanical properties. Because of the cracking that occurs, the concrete mechanical properties, compressive strength, tensile strength, modulus of elasticity, they are all going to be affected. And what we have seen that they're going to vary significantly with the principal directions. Now, with the inventory of ASR-affected structures growing day by day, we need assessment tools that would help us evaluate their safety and their predicted capacity. And so to that end, we developed a nonlinear finite element analysis procedure on how to evaluate these structures. And it's a two-phase procedure. In the first stage of the analysis, the goal is to evaluate the ASR-induced strains and the deterioration of the mechanical properties based on long-term stress conditions. Because the ASR-induced expansion is highly influenced by the compressive stresses that are developing under long-term conditions, we need to be mindful in this stage of the analysis to only consider the long-term sustained stresses. And then for our structure, we then perhaps want to know its residual capacity, its failure mode, crack pattern, the formation response. So then we can use the results from the first stage of the analysis to perform a nonlinear analysis and investigate all these parameters, these behavioral parameters that we're interested in. Now we're going to zoom in a little bit on the first stage, the ASR analysis. So what we did here, we identified several ASR constitutive models available in the literature, which describe mathematically the ASR-induced strains. These are evaluated along the principal directions. And so the user has the option to use any one of these models. At the same time, there are various options available on how to consider the deterioration of the concrete mechanical properties. For example, one of them, you may do tests in the laboratory, and so you may want to user-define them. Another option is to use the values that we get for a concrete that is uncracked, for a sound concrete, and then use ISE recommendation functions of deterioration, which are based on a value that we estimate for the ASR expansion. Both of those two options, they are considering the properties of ASR-affected concrete to be uniform in all directions. And so a notable contribution of the work that I'm presenting today is the development of an anisotropic model, which I'm going to describe to you. So what does that mean and how did we do that? We undertook an analytical program as well as an experimental program in order to develop it. And we're going to start with the experimental program, which included a material level study that was designed in order to capture the anisotropy of the mechanical properties of ASR-affected concrete. 6-inch cubes were cast with either non-reactive, reactive Spratt coarse aggregate or reactive Job-Newman fine aggregate. They were cast and they were subjected to long-term stresses under either uniaxial or biaxial stress conditions. These long-term stresses, they were applied via post-tensioning steel frames. The rods, they were tensioned up to their yielding strength. And the cubes, they were all stored in a special environmental chamber, high humidity, high temperature, in order to accelerate an inherently slow reaction. Accompanying the cylinder, these cubes were also cylinders for standard compression tests and as well as prism specimens for standard ASTM C1293 expansion measurements. So here are the results of those expansion measurements. We can see R2 and R4, those were the Job-Newman casts. We can see that they were much more reactive compared to the Spratt ones. At the end of the conditioning period, the cubes were unloaded and we extracted cores 3-inch in diameter along different directions, which we tested to compression and to tensile splitting. So here are some of the results from the compression test. The top 2 plots, they are for the Job-Newman casts, and the bottom 3 plots, they are for the Spratt casts. We can see here clear pictures of the anisotropy in the behavior. For example, if we look at the bottom left plot of the R1 cores, we can see that along the restraint direction, whether we have a 4.2 MPa long-term stress or a 2.6 MPa stress, we can see a rather significant increase in stiffness compared to the stiffness that we measured along the unrestrained or the free stress conditions. Some of the important conclusions that we could make after this test were the following. The ASR-induced deterioration was found to affect differently the compressive strength, tensile strength, and the modulus of elasticity of concrete cured in stress-free conditions. Long-term compressive stresses of 2.4 MPa and higher, they can essentially counteract the ASR-induced deterioration with respect to the concrete compressive strength along that restraint direction. The modulus of elasticity measured along the restraint directions is considerably more affected by ASR than the compressive strength. And now we're going to briefly talk about the model that we developed to characterize all this. So in the case of sound concrete that is not affected by ASR or it's just simply not cracked, we consider the mechanical properties to be direction independent. Now the directional variability of ASR-affected concrete is treated, we treat this by applying modification factors to the compressive strength, modulus of elasticity, and the tensile strength. And the way in which we calculated this modification factors was as the ratio of the reactive concrete, mechanical properties of the reactive concrete to the mechanical property of the non-reactive concrete, normalized to this initial difference at 28 days for each one of those properties. So here are the experimental modification factors that were determined from a compiled database of specimens that were not subjected to any kind of stress. So they were cured in stress-free conditions. For these cases, we decided to go with an approach in which we apply modification factors that represent lower bound values from all the compiled database. This approach is in line with the approach taken by the Institution of Structural Engineers in 1992. They compiled a similar type of data. They calculated similar experimental modification factors from a different database, however, and we can still see after all those years a relatively good agreement. Now, of course, in a structure in the field, we are not going to see concrete in a stress-free condition. And so for those cases, we are proposing modification factors for long-term restraint condition to be calculated along the principal directions. And these modification factors, they are calculated as a function of the stress in the principal direction, the modification factors corresponding to a stress-free condition for a corresponding ASR strain, also as a function of an elementary strain. And so here is now where the modulus of elasticity comes into play as well. Now, for formulations that cannot accommodate an anisotropic model, we developed an isotropic version of this, calculating the average of the modification factors determined along the principal directions. And now we're moving on to the discussion towards the validation studies that were performed. And first, we're going to discuss the validation studies performed on shear critical panel elements. 10 panel elements were constructed and tested at the University of Toronto. We can see here the test setup. They were subjected to pure membrane shear. They were cast with varying amounts of in-plane and out-of-plane reinforcement. And they were similar to the cubes. They were cast with either reactive or non-reactive aggregates stored under accelerated conditions. Here are the measurements taken on accompanying prisms. Again, the Job-Newman cast, they were more reactive compared to the Spratt cast. And in addition, we also measured surface strains on the surface of the panels along the X and Y directions. And what I want to show you here is the anisotropy that we observed in the expansion. So first, I'm plotting on the right plot. We can see with the light blue, the results that we measured on the plane prism specimen. And now along the X direction for panel number 3, we have 3.31% reinforcement ratio, and we can see that the surface strains that we measure are significantly lower. Along the Y direction, we have 0.42% reinforcement ratio, and now the strains are nearly identical to the strains that we measured on the prisms. And now for another panel cast with the same concrete, we see along the X direction that had, again, 3.31% reinforcement ratio, similar to the panel number 3. And now along the Y direction, 0.84% reinforcement ratio, we see a value somewhere in between. In terms of how we model these panels, we used a membrane element, one single element, and we can see on this plot over here the response of the experimentally measured response versus the analytical calculated one. And this is for the non-reactive panels. We see a relatively good agreement. What I want you to note here is that for the concrete mechanical properties, we only use the concrete compressive strength. And so no kind of calibration or fine-tuning was done for these analyses. With regards to the ASR analysis, we took three approaches in the way in which we treated the concrete mechanical properties. First, we use concrete strength as determined from reactive cylinders at the test date and no degradation functions whatsoever. Second, we used concrete compressive strength at test date from non-reactive cylinders together with the anisotropic model. And then third, we use the concrete compressive strength at test date from non-reactive cylinders again together with the isotropic model. We use various models for ASR expansion, but we're only going to discuss the results obtained with the Charlwood model today. And for the panel number 3, which had 3.31% reinforcement ratio in the X direction and 0.42 in the Y direction. So here on the plot on the right, we can see the experimental results as it compares with the 3 different options for the concrete mechanical properties. We can see that in terms of the concrete of the cracking strength, but all 3 approaches result in a relatively conservative estimate, with the isotropic version of the analysis resulting in the most conservative of them all because of most severe concrete degradation factors that were calculated. And among the 3, the anisotropic model matches the experimental results more closely. Here are results neglecting the ASR expansion and neglecting the ASR deterioration and expansion. And what I want you to observe here and to remain with is that if we neglect the expansion, the ASR expansion and deterioration in our modeling, we're going to end up with a much larger interval between the cracking strength and the ultimate strength of that we calculate. And so this may be a problem. Another type of specimens that we looked at were shear walls. These were tested at the University of Toronto by Habibi and Sheikh. And I'm showing here only the analytical results. In this case, using either properties from reactive cylinders or using properties from non-reactive cylinders together with the anisotropic model resulted in relatively similar responses. Compared to the experimental results, we obtained relatively accurate predictions. Another set of specimens that we looked at were shear critical beam specimens. Again, we have seen that the difference in constitutive in degradation models that we use for concrete did not play as a significant role as for the panels. What I want to mention here is that the crack propagation also was very different between the non-reactive specimen and the reactive one. For the reactive specimen, we can see that the cracks are not as well distributed as for the reactive one. The crack density is much reduced, and we managed to capture this in our analysis. And in addition, for the reactive specimens, the inclined diagonal shear crack developed at a much higher shear strength compared to the non-reactive ones. And so in conclusion, the proposed anisotropic model for the mechanical properties of concrete resulted in the most accurate predictions for specimens such as shear critical panels. However, for the walls and for the beam elements, we found similar responses, whether we are using the anisotropic model or the values that we calculate from reactive cylinder tests. And what this tells us is that for a structure in the field, material information from either damaged or undamaged concrete can be used to give us reliable numerical data for our numerical analysis. Okay, thank you for your attention.
That was a wonderful presentation. Thank you. I'm curious, it appeared that you tested most of your samples in a very high relative humidity state when I would assume the ASR gel was hydrated and expanded. I wondered if you had any idea how that would change if it was in a more dry environment.
In fact, we did not test them in a high humidity state. So what we did, we unloaded the specimens, we cored them and tested them between 24 and 48 hours after the coring. And so because these were relatively shallow specimens, 3-inch in diameter, they had the time to dry out.
Excellent presentation, really clear, nice work. So I'm just wondering, I think the numerical modeling, you do this for an existing structure, right? You have this problem, you see it on site and you want to model it to predict the capacity. How do you determine that strain, ASR strain? Do you do some like visual inspection and come up with some approximate values on site, you know?
That's an excellent question. Thank you for it. So one way to do this would be to estimate the free expansion by taking an average strain of by taking into account the crack width and the crack spacing. That's one option. Another option that I have seen is being done out there is extract a core from a region of the structure that did not expand because it was under dry conditions, take it to the lab, perform residual expansion capacity, and use that to input in your model. And a good advice would be to take a bounded approach with the worst case scenario and the best case scenario for the expansion that you anticipate.